So this is going to operate like an audiobook basically, and all credit goes to these authors over here. So I'll try to say their name: Kazuki Kawado, Hershey Gadado, Yusuke Naba, and Yura Omochi, and Shingo Masamya. Anyways, the paper is on complex network analysis of high frequency combustion instability in a model single element rocket engine combustion. And as you can see, I'm just going to read it, and it's going to be like an audiobook. The reason I'm doing it is because no one else is doing it, and I thought, if I'm going to read this, might as well make it into audiobook so I can read it, like, listen to it again. After this, we're going to make a slide as a summary, but this is going to be a later video, not this video. This video is just for the audio. So we'll start with the first page, which is over here. So Department of Mechanical Engineering, Tokyo University of Science is where the first guy came from, and then the number two is from Japan's Aerospace, Exploration Agency. Okay, that's interesting. I did not think that. Okay, that's interesting. Okay. Anyways, we'll start with the let me get my computer running. We'll start with the abstract and continue on, and then hopefully all of this gets covered in a few hours because I don't think it'll take that long. All right. We studied the spatial temporal dynamics of high frequency combustion instability in a model single element rocket combustor using an acoustic energy flux-based spatial network. The acoustic energy source collapsed by the foundation of a small communities with weak connections with a flame edge is attached to the injector rim. In contrast, large communities with strong connections are formed in shear layers between the oxygen and hydrogen jets, which, when the flame edge is distracted from the injector rim, which has a significant impact on driving combustion instability. The switching between the attachment and detachment of the flame edge during the combustion stability can be explained by a spectral cluster-based transition network constructed from the pressure and flow velocity of a hydrogen jet at the injector exit and the temperature near the injector rim. Keyword: combustion, turbulence, reaction flow. Okay, everything makes sense. So basically, they are doing some kind of new experiment with new injectors, and they're going to replace it with a shear, and it's going to form a shear layer, which makes sense from the later plots that they do. Introduction. Combustion stability is the amplification phenomenon of thermoacoustic resonant mode. Okay, there's modes here. That makes sense. When you talk about stability, there's always a mode. And it is sustained by a feedback mechanism coupling mutually among the fluctuation in pressure, heat release, and hydrodynamic in wide-ranging combustors, including power plants and aircraft and rocket engine. It is classified by um, acoustic pressure fluctuation inside the combustion into three: combustion instability. Okay, there's three frequencies that's going to be combustion. Okay, on the basic of range of dominant frequencies in the combustor: low frequencies less than 50 hertz, intermediate frequencies 50 to 1000 hertz, and high frequencies over 1000 hertz. Okay, that makes sense. Combustion instability. There's a famous name here. Lehman and Yang, 2005. They actually reference it a bunch of times. Okay. And they also reference a bunch of other authors. We'll have to see what they did later. The incident of combustion stability generates mechanical vibration of a combustor and the increase of heat transfer rate to a combustor wall, shortening the lifetime and causing serious structural damage to combustor. Okay, so there's a component that's like structural problems. Extensive and comprehensive review of the feedback mechanism have been proven and provided by Lin and Yang. Okay, Lin and Yang. All right. Huang and Yang and okay, interesting. And O'Connor. Okay, there's a bunch of other. I'm not going to read all of them. Many numerical experimental investigation of high frequency combustion stability in various model rocket engine combustors have focused on the following points relating to the driving and feedback mechanism. Should I call it I or one? I would just say I. Actually it's one because it's Roman numerals. One, the coupling of a pressure and heat to release rate fluctuation. There's a famous paper again. The mutual interaction between the acoustic modes inside the combustor and the oxygen injector. Another paper. Three, the introduction of fuel's flow velocity fluctuation due to propagation of pressure fluctuation into the fuel injector. Okay, so that's three. Then there's four now. The effects of pressure and flow velocity fluctuation on the jet flame. Okay, behavior. Okay. Five, the driving of high frequency combustion stability due to the repetition of detachment and the reignition of a jet flame at the shear layer region between fuel and oxidation flows. Okay, so there's a fuel and oxidation flow, and there seems to be okay, so that's a high frequency, right? There's different frequency levels, and yeah, so they're just saying that in the past there's a lot of numerical work on it, but that is probably because they have to like reference a whole bunch of previous works before they can actually bring the new one. So hopefully they start doing the new one, but it looks like they're going to go for neural networking, which means that we're still in that phase where the author is basically listing out a bunch of previous references because they have to for research. The complex network approach, okay, inspired by discrete mathematics, has recently enabled us to clarify the nonlinear dynamics. Okay, so of intermediate frequency combustion, instability in several turbulent combustors. Okay, there's a bunch of names. The importance of the complex network approach in the field of combustion engineering. and fluid physics have been shown in some recent review articles. Okay, yeah, those are pretty recent. These works have proactively adopted a wide variety, okay, of complex networks such as the visibility graph. Okay, well, this guy did a lot of research. The turbulent network. Okay, the cycle network. The ordinal partition transition network. Okay, there's a bunch of networks. Okay, recurrence network. So these are all just ML and spatial networks, or these are all just different types of ML, basically AI algorithms that which is not really AI, it's a subdivision AI, which is machine learning. And there, in the machine learning is a subdivision there, which is a network. But for revealing the nonlinear dynamics during the transitional state from combustion noise to intermediate frequency combustion instability, one of the most promising networks are used to clarify the spatial temporal dynamics of combustion instability in the spatial network. Oh, so spatial network has some promise. Okay, interesting. There's a name over here, and studies of spatial temporal dynamics of combustion noise and the combustion stability in a buff body stabilized combustor using a weight acoustic power network. They indicate that the acoustic power source emerge as fragment clusters during the combustion noise, whereas large cluster of acoustic power source are formed during intermediate frequency combustion stability. Regarding high frequency combustion stability in a model rocket combustor, we have recently conducted two studies. Okay, on the spatial temporal dynamics of combustion and instability in a cylindrical combustor with the off-center installed coaxial injector, including a feedback mechanism in a transitional state to combustion stability. All right, that guy shows that the scale-free structure in the turbulence network is largely maintained during the combustion stability. They also showed that the transfer entropy is valid for determining the directional dependence between the free pressure and high heat rate fluctuation that is strongly associated with the feedback mechanism in the onset of combustion instability. Schimmel, ETAL, 2021, okay, clarified that the flow velocity fluctuation in the fuel injector play an probably important, yeah. Important role in the large fluctuation. We're still in the pre-phase though, okay. Of the heat release rate, we're estimating the symbolic transfer energy, okay. Transfer entropy, sorry. They also elucidate that the emergence and collapse of the cluster in an unweighted acoustic power network occurs periodically with a generation of combustion instability. Another name. Experimenters examined the randomness of pressure fluctuation during the intermediate high frequency combustion instability in cylindrical combustor by estimating that information and to be in an ordeal partition transition network, another name, examined the directional coupling between the pressure and heat release rate fluctuation during the high frequency combustion stability in the continuous and variable resonance combustors, so using the transfer entropy. Okay, another name, have experimentally studied that the spatial temporal dynamics during a transition during the intermediate state to high frequency combustion instability in a model rocket combustor with multiple elements using a weight spatial network. A machine learning approach using based on spatial statistical linear learning theory. Okay, has Bishop 2006 has recently attracted considerable attention in the all scientific discipline that is highly expected to lead to in-depth understanding of complex nonlinear combustion dynamics and the development of sophisticated detectors of recurring of combustion stability. Oh my God. So this is good for me because now I know what I need to write if I ever write a combustion paper on instability. I need to write about all these papers. Okay. Gala and co-workers attempted to detect a precursor of intermediate frequency combustion instability in a swirl stabilized combustor using a combination methodology of an ordeal position transition network of a gel-shot complexity entropy causation plane. K means clustering and a support vector machine. The earlier detection of combustion stability in a staged multi-sector combustion and a cryogenic rocket thrust chamber has more recently been examined, both of which consider the recurring base analysis and the support vector machine. I'm just skipping the names by the way because they're saying the names are hard. So I'm just saying, just moving on. It indicate the relationship between the two interaction pressure and pressure heat release rate interaction during the intermediate frequency combustion instability and coupling swirl stability and combustor using the combinational methodology of the joint to recurrence network and Gaussian mixture modeling clustering. Okay, that's pretty good. As mentioned above, the formation and feedback mechanism of a high-frequency combustor split has been examined in many experimental and numerical studies. Okay, however, in these studies, the relevance of the interesting switching phenomenon between the attach and lift flame edge from the injector to the sustainment mechanism of high-frequency combustion stability has not been investigated from the viewpoint of a complex, interesting, network and the machine learning. The main aim of the study is to extend our understanding of the sustain. Mechanism of high frequency combustion stability in a model single element rocket combustor, focused mainly on the community detection of complex network and machine learning. Research group will conduct recent studies, okay, on the driving region of combustion stability, evaluating the energy budget of acoustic power production during the combustion stability by disturbance energy analysis. in terms of the Rayleigh index. Oh yeah, Rayleigh index. I know what that is. In this study, because I was doing deriving, if you look over here, I was deriving certain things about this text already. In this study, we first pose a local index ratio consisting of a heat release rate and a molecular production term. Yeah, that all makes sense. As mentioned above, Sherman, that's just another name, proposed an unweighted, excuse me, an unweighted acoustic power network consisting of a production of pressure and heat release rate fluctuation. They captured the emergence of a thermoacoustic cluster during the transitional state of high frequency combustion stability by calculating only the sign of the product of the pressure and heat release rate fluctuation. Okay, so we're here now. Their network was successfully extracted the periodic change in the cluster coefficient in response to pressure fluctuation, but it remains difficult to sufficiently explain the fast switching phenomenon which attach and lift frame edge from the injector during the high frequency combustion stability. The network does not particularly fail to extract the thermal acoustic damping source in the acoustic power network. Okay. Therefore, a more advanced spatial network from the viewpoint of the acoustic energy flux in the acoustic energy equation should be taken into account to appropriate deal with which switch phenomena during the combustion instability. To this end, we newly propose a class of spatial network different from the developed in the previous study, namely an acoustic energy flux-based spatial network. The division of network modes into groups community with dense sparse connection in an important approach for the reduction of coarse grain of network. The PZ map is a useful tool to identify the role of modes in terms of community and has recently been adopted to examine the dynamic behavior of turbulent flows. Nevertheless, the community detection has not been adopted in previous studies on high-frequency combustion stability in a model rocket engine combustor. A SEP for intermediate frequency combustion instability in a swirl stabilized turbulence combustor. Okay, in the study, we adopt a PZ map for the acoustic energy flux-based spatial network. We finally introduce a cluster-based transition network using the spatial clustering method. In terms of machine learning, note that similarly to the motivation of John. Okay, these names keep popping up, so they must be really. I need to look at their paper probably one day. We employ spectral clustering of unsupervised. Oh yeah, unsupervised machine learning to reveal the hidden network. Okay, so it's like a random. They probably did a lot of random stuff, but a hidden network dynamics of unlabeled physical quantities, pressure, low frequency, and fuel jet and temperature associated with the feedback mechanism of high frequency combustion instability in our combustor, rather than detecting a precursor of combustion instability used in the new data set. Okay, beautiful. This paper comprised of 4 sections. Section 2 gives a framework for the analytical method, including the brief description of the numerical computation result and discussion are presented in 3. That the findings obtained in this study are summarized in 4. And analytical methods. This name again. Computationally obtain the spatial temporal combustion field during a transitional state and the subsequent high frequency combustion stability by high resident large eddy simulation. In this study, we adopt the following analytical method for spatial temporal data. Details of the computation, including, the funny thing is, all my classes complain about we and I and so on, but all the papers I've read, all use we. So not all of them, but a lot of them use we. So I don't think it's a big problem for you to use we. Anyway, that's my opinion. Oh well. We also would adopt the implemented for spatial temporal data, detail in the computation, including the governing equation, the numerical scheme, and the initial boundary condition are described by this name again, the model rocket engine combustor. So I recently looked at Reddit and they, not Reddit, sorry, LinkedIn, and they have like a jet like this, and there was like a complaint about it not being up and down and not in English Genius or something because it's I don't know. But in my opinion, uh as long as the simulation works, it's fine. But there was a complaint on it. And I saw it, and then I was like, oh, why would they complain about that? Anyways, that's another. I'm just getting off topic. Let's just continue reading this. Detailed computation, including the governing equation, the numerical scheme, and the initial and boundary condition are described by. I already read that. The model rocket engine combustor that we deployed in the study compromised a cylinder combustor with an off century installed coaxial injector. The H2/HO2 injector is set at Y equal 472 from the center of millimeters. Yeah, I should probably say that. Center of combustor, where Y is the transversal direction of the combustor. Here, H2 and O2 are respectively released from the outer and inner injectors. The outer inner dynamics of the hydrogen and oxygen, I should have called that. Injector rim is 8.6 millimeters, which is for and then 4.9 millimeters, I guess that's for oxygen and so forth. The first tangential 1T mode oscillation with approximately 1 kilohertz, which you see the 3%, plus or minus 3%, time average pressure in the combustor are clearly produced by the computation. The flame dynamics during the combustion instability switches back and forth between the attach and lift flame edge from the injector rim, which comprise large-scale organized vortex rings. Okay. All right, first 4 pages done. Now let's look at this neural network over here. What a beautiful picture. What does that even mean? So the figure says for the A, which is the first one over here, we should be able to write over here, if I remember correctly. Draw A over here. Let's read what A is. A is time variation in spatial average pressure fluctuation, PC, during combustion stability in the region of x equals 0 at 54 millimeters y between those. Okay. And the 0 to 70. Does that make any sense? Yeah, that does actually fortunately make sense. Okay, I think it does. So range at x equals, yeah, yeah. Okay. And does that give me much? It looks like noise to me. Uh, but there must be, what is I equal? Let's see. What is I? Let's read a little bit. Read the next section has I. Oh, okay, it does kind of. Okay. And then I guess we have to read B next to actually figure things out. No, the I is not here. Oh, so this is a mystery. Wow. Let me just look at all this for a second. Give me a minute. Um, Okay, we're just gonna assume that it's fine and move on, but I think there's something I don't know about. But yeah, confusing figures always does. Who cares? Let's just move on. B is instantaneous temperature field, which is more obvious by just visually looking. You can kind of see over here the kelvins over here, which is beautiful. Oh, I see. I am blind as a horse. So over here it's like this. And over here it's like this. All right. This is what happens when you're doing it at 4 a.m. Actually, it's near 5 a.m. You just get the Dowsy. But B is instantaneous temperature field. A T in a combustion chamber in a high frequency combustion. Okay, that makes sense. And then I guess the next one is a little bit different. Uh, with I2 being something like a uh, well, it's still kind of well, it doesn't really. It's is it both high frequency? Looks like it. T equals 32. Okay. All right. Another name and shedding from the injector rim, figure 1B. The location of the frame edge during Z equals 50 millimeters. When the frame edge is lifted from the injector rim, where Z is the longitude direction of the combustor. The ignition of the unburnt hydrogen and oxygen mixture periodically rise shortly after the unburnt hydrogen oxygen mixture that moves upwards and touch the high temperature combustion produced. As a result of the periodic ignition, the attached flame forms near the injector rim. We focus on the regions x equals 0 millimeters and so on and so forth, and then covering the flame dynamics and high frequency combustion stability. All right, now the Rayleigh index ratio, which remember correctly, it's not properly derived, but I guess he assumes we know it, which is fine. I'll explain it in the slides later when we actually do it. It comes from Navier-Stokes with a little bit of assumptions over here and there. If you took a little bit of Dr. Sanchez's classes, you'll understand it. And that's about it. Excuse me. The Rayleigh index, which is derived from the acoustic energy equation, is widely used as an important indicator for extracting the driving region of combustion stability. Namely, explains that the molar source term considered a change in the number of moles in the gas to chemical reaction work at one source term in the acoustic energy equation on auster combustion. Our name shows that the energy budget of the acoustic production show that the considerable estimate of the Rayleigh index on these basics we here's it. Where was I again? Show that the energy budget on the acoustic production should be considered for the estimate of the Rayleigh index on these bases. We propose that the Rayleigh index ratio consider the effects of the heat release rate and molecular production speed as the source term in the acoustic energy equation. In this index, we define the source term as phi. As 2.1, the second term on the right side of 2.1 correspond to the heat release rate source term, molecular production source term. Yeah, that makes sense. I've analyzed this in the slides because they really didn't. But basically, what you're doing is basically starting from the inviscid equations and going into the perturbation and then going into all this stuff. I'll do this later. I'll explain it more carefully later when we do the presentation. But as you can see, there's a source term over here, and this is a full equation. And as you can see from just looking at it, to be unstable, the source term is the main effect. Yeah. And you can kind of see that there's two versions of it. There's a heat release over here, and then there's the mole stuff over here, which makes sense if you think about it. This is going to, no, no, this one. This is going to be the heat release, and this could be mole because there's an N there, obviously. Clearly, N means mole concentration in different areas. That's what we use it for here, right? It's not obvious actually, but all right. Here, these two variables of R is the local Rayleigh index based on, so they're averaging it basically on the heat release rate source term, molecular rate state. This A, this I don't know what's called, the zeta I think, or maybe the mu, I don't know. It's a local Rayleigh index ratio, yeah. And we know the heat ratio, right? Specific heat ratio. That's the gamma, and pressure is P inside the combustor. Q is the heat release rate. So here's a really cool thing. In a lot of in Dr. Sanchez would estimate the combustion as Q, and basically that's what they did here, and that's how they get the equation over here because that's what I had to do to get the same thing. I even wrote call Dr. Sanchez notes because you're gonna have to just do similar to MA 201. Yeah, so we're gonna basically say the combustion is just gonna be small q. Yeah, basically that's how this was defined. Is it the best way? It's easy to model. And from what I know, a lot of these models already have like a 10% error. So that's what I heard. It might not be true, but that's what I heard from people. And then it even says N is the mole concentration. So it's kind of obvious. N dot is actually this equation here, where NS is a total number of chemical species, and species is different chemical. M is the molecular weight of a species I, and the W dot is a no, is a production rate of the species I by the chemical reaction. And there's stuff, but one represents the time average of the fractional quality, the physical meaning of the data or whatever this is. Symbol is the mole production source does not affect the driving of the combustion stability, where I'll just call it theta for now. Equals unity. R equals 0. The mole production source acts as an amplification of they even parentheses anti okay of combustion stability where zeta is larger, smaller than unity. Okay, note that the TP is used to 10 meters per second in this study so as to limit the dependence of TP and spatial distribution of R and zetas. I have a feeling that they okay, that's interesting. Acoustic energy flux based spatial network. So now we're going to get into basically the kind of the framework of it. So Kerman and Sherma studied the formation and collapse of the acoustic powers in the source power network over here. In the study, we proposed that an acoustic energy flux-based spatial network is a new complex network. Let us assume that the total acoustic energy source produced at the local region, delta y, delta z, can be expressed as phi, delta y, delta z. Our network considers the energy flux ij underscore ij at location y, yj induced in the acoustic energy source phi ya per unit time volume at another location yi as follows. Here, delta, the deltas is the grid spacing in yz direction over the Cartesian domain. Luckily, it's not polar, otherwise it's going to be a little bit more confusing. It'll still work out, but it'll be more confusing. And the grid corresponds to the node of the network. Equation 2.5 physically means that the energy efflux propagate to a location r away from delta delta when the delta y delta z. When the total acoustic energy spreads isotropically on the basis we define the weight as a link between nodes. Okay, I need to get the other section now. R. So where Wij represent the mean energy flux between I. So basically you transpose it basically, I guess. Which, okay, it's not really a transpose because it's not really like that, but you get the point. All the indexes just change. And then you get I underscore ij plus I underscore ji, and then divide by 2, and then you have a W, which I'm guessing is some kind of weighted thing. I mean, constructively network consists of the weighted adjacent matrices, plus and minus, plus and A minus. All the nodes, except for I equal J, are connected to the first network. The node in the second network, third network, are connected when phi yi is greater than 0, phi, parentheses, phi yi is less than 0. Because you're doing those mixing things. Corresponding to the amplification for acoustic energy, we estimate the node strength S. There's a bunch of S as follows. So here's the estimation of everything. It's like just a system equation over here. Kind of see what that means. And then S is basically just a summation of all those. Here N is the number of nodes, and N is equal to 19K basically in the study. Okay, this author, we're doing community detection, which is quite interesting. And then, all right, I think we could stop. Why don't we just finish? Okay, so I've recently extracted the community in the turbulence network during intermediate frequency combustion stability in a swirl stabilizer combustor by the Lovan method based on the molecular optimization. In the study, we adopt the Lovan method for the acoustic energy flux-based spatial network. Nguyen proposed that the molecular Q is an important index of the division accuracy of the community. We extract the community by computing the gains to delta Q obtained by moving the isolated node I into the community C AK as its formula over here. Here M is the sum of the weight of all the link on the network. So this is a little confusing because this is going to network thing, which is a little different, but than stability. But it does make sense to me because it's just basically machine learning. It's the sum of the weights of the link from C to something. You see this formula, it's just explain the formula. It's sum of the weight of the link is into the node of C and S, and the sum of the weight of the link from node I. The other node is the C, and the delta is the quantum delta. Suitable total number of community is determined at the maximum of the morality, which Q becomes maximum when the sign of delta Q changes from positive to negative. All right, and this other author proposed that P to Z map as a useful tool to understand the spatial complex network. Another one, Mida and Carella, studies the spatial temporal, what is it? Spatial dynamics of the vorticity. Uh, Vorticity structure by examining the PQ of the turbulence network. In the study, we adopt the PQ for the acoustic energy flux-based spatial network. We first define S as a node of I, the summation of the weight of the link adjacent to the mode in community C. As you can see by this equation, we have S. Here, C is the community of the node belong to C prime or whatever the hat. In the set of communities K, the participation coefficient PI and the within community degree Z score ZI are respectively given by 2.14 and 2.15, where SI equals C and the sigma is the mean value standard deviation of SI. As you see over here, those are the equations. I think they're pretty self. Just look at it. That's just it. Which I'm talking about these equations over here. Equation 2.14 and 2.15, where NC is the total number of communities and ZI is represented by the degree of connection between node I and the other node at the same community, where ZI takes the high value. Node I is strongly connected to the other node and becomes a hub of the community as PI is a high value. A node is homogeneous connection with all the nodes in the community. Note that 0 is less than PI and then greater than, no, less than 1 and then greater than 0. This is just probability analysis. It's not anything special. All right, now spatial clustering is next. Spatial clustering is a useful unsupervised machine learning method that's performed by applying the k-mean method of the eigenvalue of the Laplacian matrix and complex network. In this study, we first construct a three-dimensional plane consisting of the pressure flow and flow, velocity for the hydrogen jet at the injection exit, and the temperature near the injection rim. The latest space with K cluster is obtained by applying the structural cluster method and the Gaussian kernel transformation of the three-dimensional plane. We finally obtain transition network of a cluster from the latent space. The value of K is set to 12 in this study. All right, results and discussion. Figure 2 shows the spatial distribution of the R's, the Rayleigh indexes, and this ratio. I should call it this ratio, right? During high frequency combustion stability at the 30 milliseconds T, and it has to be between 30 and 40 milliseconds. Okay. The value of the Rayleigh index of, should I call it Rayleigh index? Yeah, I should call it Rayleigh index, but I should be calling it the Rayleigh index of the heat rate. So the heat rate on this one, so I should call it the Rayleigh index of heat that is larger than 0 along the shear layer region between the hydrogen and oxygen jet. Yeah, that's because that's a mesh, right? So there's like a oxygen layer and there's a helium layer and there's oxygen. Oh, wait, that's not right. If I remember correctly, there's a helium layer and then a hydrogen layer, an oxygen layer, then a hydrogen layer. So that would create a basically, how do you describe it? So basically what's happening is a classic question where you could probably solve a lot of this on your own. Basically, what's happening is that there's like a jet input, so there's a face over here. So what's happening is that there's a face. So there's like a layer that you could go. So I wonder what boundary conditions that she could the paper used. Probably nothing. Instead, they use like a CFD. Yeah, they probably use homebrew CFD instead. So if you didn't know, the way you solve it analytically is by making what do you call it again? A phase mesh. Like you would put the like phase mesh here, and so on to indicate that there's like it's like different density, different fluids. Like if you have like one fluid here, you have another fluid here. The interaction between those two fluids creates a phase layer, the like a mesh layer, and that you need to it's a phase, and you need to get it with the analytical solution. Anyways, let's just move on. I'm confusing everyone. All right. The value of the Rayleigh index of heat is larger than 0 along the shear layer region because hydrogen and oxygen jet reveals the driving region of combustion stability as a result of the production of the acoustic energy due to strong mutual coupling between the pressure and heat to release rate fluctuation. In contrast, the Rayleigh index molar one, so this is the molar concentration, is less than 0 among the shear layer region, indicating that the mutual coupling between the molecular production and pressure fluctuation actuates the combustion instability. Okay, the value of this ratio is approximately 0.9, which shows that the molecular production term contributes to a decrease in the acoustic energy and originates from the heat rate release rate term, and this ratio also decreases in radial direction. So this makes sense. What it's basically saying is over here, molecular did nothing. Over here, you see all the values over here. So right now, what's happening is molecular production is help dampen the acoustic instability. It doesn't drive it right now, so it's pretty good if it's 0.9. It's dampening it a little bit. Well, according to my little bit of analysis I did about this paper like a few weeks ago. Also decrease the radial direction. That means that the attribution of the acoustic energy due to molecular production is greater than the hydrogen region. Then, okay, I already read that part. Over here. So we could in the oxygen jet view. Okay, so we're gonna have to analyze the uh graph a little bit. Spatial distribution of the local Rayleigh indexing A. Okay, Rayleigh indexing based on the heat release rate term. B Rayleigh index molecular based on the molecular production. Okay, term. So they're basically you can see what's going on. They're splitting it basically. And C is a local indexing ratio during the high frequency combustion between. Okay, yeah. So this is the most impactful, I think, then, because this is a phase plot of one R, which is the Rayleigh index, and another Rayleigh index. It doesn't show the combined. So here's the combined version. So this is incredibly, I think, more useful. Hopefully, I'm not wrong, but in my opinion, that probably is the most useful. Although it does show, so that's interesting. It's not symmetric. You can see over here, there's not a symmetric. I wonder why. Because if you think about a jet that's basically same in both sides, you would think the output would be the same no matter what you do. But there seems to be some decrease here. So maybe it's because of gravity that you have this problem. But then again, in the equations, you never see a gravity term here. So I am slightly confused on why that would happen. It's an interesting question. I don't know the answer to, but where's the equations? Here again. So production term, Q term. Well, in my derivative, there was how you derive it is over here. There is literally no gravitational term. So maybe she added a gravitational term somehow? That'd be a question. Or it could be something like an initial condition that makes it different. It's a really good question. I don't know what's going on here. Maybe the machine learning did something about it because of the network structure of high frequency combustion stability. So maybe what happened was the machine learning kind of look at real data instead, and then look at the equations and repeat back to these equations. I don't quite know. So quite a questionable one. Anyway, let's continue reading. The dampening effect of the high frequency combustion stability, approximately 10% with respect to the heat release rate term, is non-negotiable for inferring the driving region of the high frequency combustion stability, which supports the importance of the molecular production term explained by Louis. These results demonstrate that the local Rayleigh index ratio consists of a heat release term and molecular production term and is significant for interfering the driving region of high frequency combustion stability in a model rocket combustion with a hydrogen oxidation injector. Figure 3 shows that the time in variation in the spatial average pressure fluctuation PC, heat release rate fluctuation Q, and node strength S plus minus S plus and S minus I indexing is all indexing during high frequency combustion stability in the range of x equals 0 and 64 to 80 millimeters and 0 to 70. Okay, millimeter. We observe that PC fluctuation periodically, whereas Q exhibits intermediate fluctuation responding to the attachment and detachment of flame edge from the injector rim. Node strength S plus or minus I exhibit periodic fluctuation with half the period of PC and increases when the PC takes a local value. And S plus or minus markedly increase when Q changes owing to the detachment of the flame edge. An important point to emphasize here is that the S plus is considerably larger than S minus in the indexing. When PC takes the local minimum owing to the detachment of the flame edge, these results show that the acoustic energy production is promoted when the flame edge is detached from the injection rim, resulting in the retention of combustion stability. The spatial distribution of S plus and minus and indexing are shown in figure 4. So figure 4 is later. Figure 3 also shows that. So what is going on here? Figure 3 is, okay, it's way later. So they're just bobbing again. Okay, together with the power distribution of the node strength, PS minus, the node with high strength are distributed among the shear layer at time 32.55 milliseconds. The coefficient of determination of R squared for P S plus minus, P S plus, and P S exceeds 0.9, the scale free. Oh, wait a second, wait a second. This could be some kind of a convection thing that could have happened. Wait a second, it could be something like some kind of convection thing that rolled off over here. That could be something which would be indicative for this region over here. Interesting. All right. That could be true. That could be true. That could be the reason why it's such a real difference. But the coefficient of determination R squared, okay. The scale-free nature appears to be all following institution of node strength. The scale exponents gamma s for PS plus minus, PS plus, and PS minus are 2.6, 2.8, and 2.4, respectively, which shows that the existing probability are the hubs are almost Okay, the same. Now let's read this and analyze the graph. Time variation in the spatial average fluctuation. Okay, so the time average, yeah, that makes sense. PCAQ time average, that makes sense. And then this is what's the axis? Uh, PCQ, yeah, that makes sense. And then red is the Q, that's interesting. And then this is 30 to 50, which we discussed is probably some kind of indexing. Yeah. No strain periodic test, yeah. Okay. And then and B, time variation of the average mode string in the acoustic energy flux-based spatial network during a high frequency combustion instability. Okay, that makes sense. That doesn't make sense. What's going on? Well, it looks like the first term is basically talking about those two, and then the second term is talking about the node status, average node strength, which is derived equation over here. So it's going to be talking about these two, these not this one, this equation over here with this equation. Um, yeah, that's mostly for the networking over here. This is actually for the and networking, pretty sure. You need to do a punishment scheme for neural networks, so that makes kind of sense. Okay, we'll move on here. Here. Yes. This means that the acoustic production and the dampening source are equally formed when the flame edge is attached to injector rim. In contrast, the scale-free nature of P's collapse at T equal 38.25. An important observation is the expansion of the formation region of the node with high strength, including the experience of a large-scale primary hub. This means that the formation of the large-scale acoustic energy source drives combustion instability with the flame edge is attached. The result shown in Figure 3 and Figure 4 indicates that the acoustic energy flux-based spatial network proposed in this study enables the production of the acoustic energy source with accompanying intermediate heat release rate fluctuation to be captured. In this paper, we have presented the spatial distribution of the local Rayleigh indexing and the ratios during 10 cycles. The high frequency combustion. Oh, now here's what I was missing. That makes perfect sense. All right, that just makes everything makes sense now. The acoustic energy flux-based spatial network, which enables us to instantaneously extract the acoustic energy source, is superior to the local Rayleigh index in the sense that the acoustic energy flux-based spatial network can be capture the subtle changes in the acoustic energy source in response to the flame behavior with fast switching between detachment and attachment on the injector rim. Note that the coefficient of the network structure used during node strength, yeah, that makes sense. Which now this paper is making total sense now, which identifies both the amplification and attention region of the acoustic paper has not conducted in previous studies on the combustion stability. Figure 5 shows the community that the PZ map at the time of attachment of the flame edge to the injector rim here, PI and Z max, is mean maximization of PI and ZI in the community CAK. The black marker corresponds to the center of CAK, and the plot size represents the sum of the node strength in the community. The width of the gray line represents the degree of connection between the communities. The small communities are formed along the shear layer. The connection between them is strong near the injector rim and weakened downstream. Some communities take high-low PI and Zmax value near the injector rim downstream. This means that the community possessed a hub near the injector rim, where else it vanished downstream. So with the formation of an isolated community, these results show that the acoustic energy source induces near the injector rim collapse downstream, and the flame edge is attached to the rim injector rim. The community ends. Okay. And the PC mapping at the time of detachment of the flame edge from the injector rim is shown in Figure 6. Okay, so here is network structure of the high frequency combustion instability. Oh yeah, this makes sense. This is classic basically regression streams to see if the neural network has any correlation. And as you can see, the more linear it is, the more of those lines over here, which is over here, the lines over here, the more correct we are. If there's a correlation between them, we're correct. It seems like there's also a correlation here. This one is a little problematic. This means that there's a term there that's not perfectly aligned with the specified way of looking at it. This over here, yeah, that's a problematic issue over there. All right, figure 4, spatial distribution of a node strength. Although it does indicate something of a correlation between them. It doesn't mean there's no correlation, but correlation also doesn't mean a causation and probability, as everyone knows. But it's all neural networks are probability based here, so that's pretty sure. Probability distribution of the node plus strength of P's and acoustic energy flux based neural network during the high frequency combustion stability at 32 and 38. Wow, so there's a much more higher correlation at T equal 32.55, and when you go a little further at 38.25, the correlation doesn't really indicate too much. And also, I love that it's symmetric. It does imply that it is kind of doing the right thing, to me, in my opinion. Communities appear downstream at 37.55. Large communities with strong connection are formed along the shear layer when PC and Q take a local maximum at T equal 38 milliseconds. I might be wrong about that. That's just my indication because they did talk about it being symmetric. But obviously, there's something that's not causing that symmetric to be true. Um, I will reread this again and hopefully find out what's going on. And the next presentation, when I figure that out, will be when I figure it out and I tell you guys. All right, to the formation of the large communities is attributed to the V-nation upstream during the flame edge moving downstream. Connection between the communities weakened. As t equal 38 to millisecond 38. Okay, so these seconds actually matter. I was rounding up. It was 37.75 milliseconds earlier, and now it's 37.95 milliseconds. Where else is the strength again with PC and Q takes a local minimum at 38.25 milliseconds. Communities with the highest Zmax is formed at t equal 37.75 milliseconds, compared with those at t equal 38.25, which indicates the appearance of a dominant hub in the communities due to ignition of hydrogen and oxygen flames when the pressure and the release rate fluctuation takes a local maximum. In contrast to the communities of the high P's are formed at time equal 38.25 compared to those at the time equal 37.75. Milliseconds are indicating that the movement of the flame edge downstream causes the connection of the community to strengthen. Oh, yeah, I should do more of these, like read along. But anyways, here's another network. So communities, A is communities. Okay, B is the PZ mapping that attached time frame to the injector rim during the high frequency combustion stability here at time equal 32.55 seconds. So this is a transformation. Interesting. It's not bad. I see some clustering, which means we might be doing, I'm pretty sure, what we call unsupervised neural networks, and it looks like it is doing that in the future. Yeah, it seems like we're doing some clustering, very much, a lot of clustering. That's gonna be fun. Okay. I can explain that in the presentation. We'll explain that later. When with the pressure and heat relation local minimum, high frequency combustion stability in the study is maintained, accompanying the change in these community groups and structures. The Indian Institution of Technology Models Group and other groups have conducted detailed experiment studies on the emergence and collapse of the cluster of the spatial network during the combustion stability in the Pluff body stabilized combustor and a model walking combustor with multiple elements. All right, we're continuing off here because my video got cut off again. All right, so one of the authors, Murdra, has also conducted an experimental study on the formation of a primary hub in the turbulence network during intermediate frequency combustion stability in a slow stabilized turbulent combustor. The community detection uses the acoustic energy flux-based spatial network is expected to be helpful for understanding the spatial temporal characteristic of the cluster and their connection during the combustion stability in various combustor. A lot of the flame dynamic depends on the chemical and the flow characteristic timescale and the configuration of the combustor. Figure 7, which is the next, which is it's really weird. The next figure is figure 6, but we also mentioned figure 7 now. It's just really, they keep on doing that stuff. I don't know why. Shows the time variation of the temperature near the injector exit. Okay. Note that the temperature of Z is 0.46 is extracted the represent location and abrupt increase in temperature is intermittently observed in the range of 68 to 76, showing the inflow of combustion, the product of a hydrogen jet near the injector rim. This is strongly associated with the reignition of the hydrogen and oxygen mixture. Mr. reported that the decrease in the flow velocity at the exit of a hydrogen injector generates the inflow of combustion products into the injector. Shima has recently clarified that the pressure fluctuation inside the combustor significantly affects the flow velocity fluctuation in the hydrogen injector. On the basis of these findings, we examined that the structure of the spectral clustering-based transmission network constructed from the pressure PE at the exit of the hydrogen injector, the flow velocity WE of the hydrogen jet at the exit of the injector, and the temperature TR near the injector rim. Okay, that's beautiful, but let's look at the graph and figure out what's going on here. So they gave us a bunch of scales over here, which we read earlier. So figure 6, the variation of a community P2Z mapping at the time detachment of the flame edge from the injector during high frequency combustion stability. So AI, BI, T equal 37.55 milliseconds, T equal 37.75 milliseconds, T equal 37.95 milliseconds, and T equal 38.25 milliseconds. So looks like it's some kind of clustering algorithm, which is beautiful. I mean, it does make sense. They would do a clustering algorithm, and it's unsupervised probably. So oh yeah, here we go. So yeah, it's just transform, 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 and so on and so forth at these regions over here. I'm sure they're trying to get a pattern here. So there hopefully is a pattern soon. Okay, I don't understand why they keep on showing a figure that's 2 steps ahead of you, because next figure 7, the figure 8 is like next page. But I don't care. Figure 8 shows that the latest spatial consisting of WE and PE and TR and the centroid of the cluster CTR in the latest phase high frequency combustion together with the transition network between the cluster. Note that in the study we define WE, WE, and PR as a spatial averaging values. Okay, yeah, obviously, if you don't know, these brackets means averaging. So if you ever see these brackets, that means averaging. I didn't know that for a long time, but I usually use a bar on top, but that gets confused for a vector. So don't either one works. You just have to like get the nomenclature correctly. Central latent heat combustion reactor with the transition network of the cluster. Note that in the study we defined WE and PE and TR as a spatial average value of WE, PE, and TR at these points. I'm not going to read those points because it's going to be just numbers. I can just say 68.4. No, I'm not doing that. Here, these three at a certain cluster, I think, because it's underscore C, probably. We'll see. Correspond to central. Oh, it's centroid, okay, of the cluster. And the width of the gray line of the network represents the probability between the cluster. You see, here's a problem. This is the next figure, but you guys are talking about this. This is what you're talking about, and then but the description is over here. Why? Probably between the cluster. Then they're not going to it. Okay, figure 7. Time variation and temperature T near the injector exit during the high frequency combustion stability here as Z equals 0.46. Excuse me. Makes sense. Okay. And the Z equals 0.46. To me, it looks like a number that I quite frequently looked at for some reason. Uh, It said Z equals 0.46 millimeters. Oh, I remember seeing that earlier. I mean, because yeah, it's probably one of these things. Yeah. Mm. Yeah, makes sense. Okay, that makes sense. Okay. Yeah, the description was earlier actually. So what's happening here is that there's 0.046 is okay, that makes sense. So what's happening here is that you're going to 0.46 about this range over here. Interesting. Why would you do that? Well, you probably want to just one place that you can just look at. Anyways, okay, that's 0.46. Where was I reading? All right. With the cluster, all right, yeah, cluster. All right. The network exhibit two phenomenal orbits. I think they mean one. One cluster 1 to 2 to 3 to 4 to 6, and cluster 2 and 2, cluster 6, 7, 8, 9, 10, 11, 12. And that's over here, if you know, I think this is what they're describing, I'm pretty sure. Two exhibit here. Yeah. 1, 2, 3, 4, 5, 6, 7, 4, 5, 6, 7, 8, 9, 10. Yeah. Yeah. They are connecting to each other at 6 cluster. The central node of a cluster of the temperature TRC, which is centroid temperature, remain unchanged in orbit. Oh, that's interesting. One, whereas it changes over 2. This indicates that cluster 6 corresponds to the critical state of the detached flame edge from the injector rim. We observe that the temperature in the rim of the centroid takes a maximum value at cluster 8. On the basis of the shown in figure 7, cluster 7 corresponds to the inflow of the combustor production in the hydrogen injector near the injector rim of the subsequent reignition of hydrogen oxygen mixture. An important point in that the trajectory of the cluster bifurcates at cluster 6. Bifurcate. So there's also a bifurcate diagram where you can bifurcate means like the pitchfork like this. No, this doesn't have that, but bifurcate means something like that, which we could draw at cluster 6, really. Okay. Takes a positive negative value of cluster 1. I wish he'd do the bifurcation of but he didn't. This means that the subtle changes in the flow velocity of the hydrogen jet at the injector ester has a significant impact on the triggering of the bifurcation in the attachment and detachment of the flame edge and the onset of the intermediate heat release rate fluctuation during the high frequency combustion stability. Note that the cluster 6 is the bifurcation point for the sudden switch between the attach and the lift flame edge, but the dynamic behavior of the pressure does not notably change before and after the bifurcation. These results demonstrate that the spatial clustering-based transition network is used for understanding the physical mechanism of the high frequency combustion instability in a modern rocket combustor with a hydrogen oxygen injector. All right, now 4 is a summary. I had so many complaints about this paper, but overall, it's just a structure. It's nothing more than a structure. We have a study of spatial temporal dynamics of high frequency combustion stability in a cylinder combustor with an off-center installed coaxial region related to the hydrogen oxygen rocket combustor from the point of view of the complex network and machine learning. Focus mainly in the production of acoustic energy source, said the molecular production induced by combustion reaction affected the allocation of the combustion injector, which is shown by a local Rayleigh index ratio. I should call it Rayleigh index ratio. That's probably better. Consider that both of the heat release rate and molecular production term, the pressure inside the combustor oscillate periodically, whereas the heat release rate exhibits an intermediate fluctuation responding to the attachment and the detachment of flame edge from the injector rim. The acoustic energy flux-based spatial network we propose in the study enables the appearance of acoustic energy source with accompanying intermediate heat release rate fluctuation to be captured when the flame edge is attached to the injector rim. Nodes with a high strength are formed in the upstream region of a high shear between oxygen and hydrogen jet, exhibiting a high free nature in the strength distribution. The acoustic energy source collects by the formation of a small community with weak connection, in contrast to when the flame edges, I didn't really. Okay, here we go. Edge is detached from the injector rim. Nodes with high strength are widely formed in the downstream region of the shear layer, revealing the loss of the scale-free nature. So here's a diagram. So A is latent space consisting of spatial averaging pressure at hydrogen injector exit, the flow velocity WE of the hydrogen jet of the injector exit, and the temperature TR. So this is like an interesting cluster analysis that they did. Near the injector rim during the high frequency combustion stability, B is the centroid of the cluster CT T in the latent space, and C is a spectral cluster-based transition network. Okay. So this edge is detached from the injector rim, and nodes with high strength are widely formed in the downstream region of the shear layer, revealing the loss of the scale-free nature. The formation of large communities with a strong connection has a significant impact on the driving combustion instability. The switching between the attachment and detachment of the flame edge during the combustion instability can be shared by the spectral clustering-based transition network constructed from the pressure flow velocity of the hydrogen jet at the injection asset, the temperature near the injector rim. The two present analysis I1 community detection using the acoustic energy flux spatial network, and two, spatial clustering as a form of unsupervised machine learning are useful for understanding this complex complex spatial temporal dynamics of the combustion stability. Here's figure 9, variation of the average clustering coefficient as a function of the class number K during a high frequency combustion instability. Whew, we're done. Appendix A, class number of the clustering-based transition network. We determine the suitable class number K of the. This is just extra. Transition network by instrument 2 coefficient. The way. Okay, so this is a clustering I, and then here AT is indirectly. Okay, so matrix A. Yeah, yeah. Oh, yeah. And then this is a classic neural network. Yeah. On the directed adjacent matrix, the value of NT is 500 study. Okay. Figure. What's figure 9? Where's figure 9? Oh, figure 9. Oh, you're explaining figure 9 over here? What is wrong with this structure? Something definitely is wrong with this paper. Maybe they when it was translated maybe from China, maybe it was translated from Japanese to English and it just got fucked. Anyway, figure 9 shows the variation of the okay, so average clustering and the high frequency. Oh yeah, this is just basically just stating no the like what you're doing over here, which is like just stating that. All right, I'm gonna stop the video, but that was fun. And I'll make a presentation because but actually, maybe not. Maybe I'm a fool. I'm probably the fool. I'm just gonna present. I'm gonna analyze this and try to figure out why some of the things work, like what I was doing earlier. And yeah, we'll make a presentation on it. And then obviously all credit goes to these people again. These are the ones I give credit to again. Uh, yes. I should make this bold. Like these are the people I should be giving credit. I'll make the redo the title to emphasize those authors. All right, let's stop recording.